All right, welcome back. Now we are going to talk about some other terminologies and some following examples for first law. Okay, so we are starting with um, specific properties. Specific properties. This is basically very easy. You just divide something by mass or number. So, for example, like specific volume or specific internal energy, or yeah, these are all specific properties. So, you add this bar, under bar, to certain properties, and it will be U. So, you can call it either specific property or molar property. So specific internal energy equals U divided by mass. This is the total internal energy. This is the mass of the system. So let's say there is this kind of copper crystal, and these are copper, and the mass of the system is maybe 5 kilogram. Internal energy is 100 joule. Then specific internal energy is going to be 20 joule per kilo. So joule per kilo is the unit for internal, specific internal energy. And for molar use, that you can also write it like this, is U divided by N of Cu. So let's say in this system there is 5 mole of copper. Then it is also going to be in order to prevent you guys from getting confused, let's change this to 20 joule, no, 10 joule. Then it's going to be 10 joule per mole. So joule per mole is going to be the molar internal energy. You can also use it like molar gives free energy or specific gives free energy. Um, Enthalpy, this is enthalpy, we're going to learn later. Specific enthalpy, molar enthalpy. Anyway, so why do we do this? This is because, uh, first of all, we have to talk about intensive and extensive property. Extensive and intensive. So this word comes from the word extent. So it means a certain property is decided by how much it has. Like depending on its dependent property, dependent on quantity, right? Intensive is the opposite. So let's say there's this system and it has a volume of 5 cubic meter, and this system has a volume of 2.5 cubic meter. It both has, it's both copper system, right? Like this. It both have no, so this one has 8 mole of copper. This one has 4 mole. Then what is the specific let's use molar here. So molar, what is the molar volume? Then it's 5 divided by 8. This is 2.5 divided by 4, which is going to be same number. So as you can see, volume is extensive property because the more the more copper there is, like when the number of copper is twofold, then the volume is also going to be twofold. So volume is dependent on the number of copper. And as I am emphasized many times, we are learning thermodynamics for materials, so we have to think about the intrinsic property of the material. So when you think about this case, nothing has changed other than the number of copper. So the property, the intrinsic property of this copper doesn't change. The only thing that changed is the quantity. So you have to normalize this. Normalize. So when you normalize this, you'll see that the intrinsic property are the same, right? So in order to see the intrinsic property of the material, we have to normalize this kind of extensive properties, right? So because these properties depend on quantity, so we have to normalize this in order to compare. So if this was not a copper, if it was a different something like iron, then it would have different molar volume, right? Same logic goes for internal energy. So if same condition, the only difference is the number, then copper crystal will have the same internal energy for both cases. But if we either increase the temperature or increase the pressure, or even just change this crystal into some other crystal like iron or aluminium, then the internal energy and then the molar volume, they're all going to have different values, like way different. So this is how you compare materials, by turning extensive properties into intrinsic property by normalizing it. Okay, our goal is to have all the intensive properties. You can think of it like this. So we have to think about what is the example of intensive properties. Well, it's something like temperature or pressure or density, right? Because the number of this copper crystal is not going to change the temperature or pressure, right? This is tricky, but when you think about it, even if there is 100 mole or 1 mole, if same kind of intermolecular distance, then it's going to have same pressure. Like no matter how big the size of the crystal is. So pressure, something like pressure or temperature, are all intensive properties. It's already intrinsic to the material. You don't have to normalize them. And also same logic goes for density, because of course density is already normalized, right? Like m divided by volume. And here you can remember this. So rho equals m divided by v, and specific volume v under bar v is equal to v divided by m, so which is the reciprocal of density. Now we don't have to use this now, but in later lectures, this is going to be very useful, this relationship. So I suggest you memorizing it. Okay. So much for specific properties. And remember that here, so you divide it by mass or number, right? This is practically the same thing. In physics or science, you have to think of this concept as very, very similar concepts. Like mass is just another expression of quantity. They are both an expression of quantity. Let's just put it like that. So quantity can be expressed by actual number of the molecules or the mass of the total system. They are going to be proportional. Yeah, like this. Okay. Now, let's talk about steady state and equilibrium. So, long story short, they are very, very similar, but the relationship goes like this. So, this is steady state. This is equilibrium. This is the relationship. So, what is steady state? Steady state definition of steady state is that the system doesn't change with time. So, as time goes by, delta U equals to 0, delta S equals to 0. This is entropy, by the way. Delta H equals to 0. This is steady state. Steady state. And then what is equilibrium then? So what is the difference? We can think about diffusion, right? So I don't know if you guys already learned diffusion or not, but so this is C, this is X. When you think about this area, this is first Fick's law. You will learn this in thermodynamics of materials number 2, but here I'll briefly explain it. So the first Fick's law is for steady state cases. And the temperature gradient doesn't change with time. With time. So, like in this kind of situation, then amount in equals to amount out. So in this region, it's like it doesn't change. Number of inside is constant. This is steady state. And what is equilibrium then? This is equilibrium. What is that? There is no temperature gradient. So of course, number in, number out still remains the same because there's nothing coming in or going out. And you can see that's how this kind of relationship is made. Now this equilibrium and steady state is a very important concept. We are going to assume a lot of cases in cases that are steady state for simplicity, okay? For simplicity. So we are going to assume it. It doesn't mean it's like them. In general cases, it's not steady state or it's not equilibrium, but we are going to just assume it is going to be steady in order to learn first, in order to study the concept first. Okay? So uh, let's think about this kind of an example to better understand what is steady state. Mm. Okay, moving on. Sorry. Moving on. Now, we are going to talk about enthalpy, which is defined like this. H Q no U plus PV. Okay, this is a very important uh, important section, so I hope you understand it. And anyway, so let's go back to first law. U equals delta U equals Q plus W, right? First law. And I told you that Q is a path function. Now, we already know how to change this into state function. I told you that is the strategy, right? I told you in the last lecture that we want to change both of these path function into state function. That is the strategy in order to, what is this? Sorry. In order to make the calculation more convenient and in order to accurately calculate maybe the energy of a heat engine or something like that. So in order to calculate anything accurately, we have to change these two into state function. And we already know how to do work, because work equals minus P external times delta V. And these two are all state function. So when we know some kind of route, we know the route, we know the expression for this, PV graph and this kind of route, right? And we are going to know this as a function, right? P is going to be FV, as V change, P change, right? And if we know what kind of route we took to do this kind of work, then we can simply calculate work like this, right? As we talked about in the previous video. So we already dealt with work. Now we have to think of a way to change this Q. Okay? So that's why we introduce new concept, which is enthalpy. H equals U plus PV. Why? Let me explain. This is very fascinating. So Q has a physical meaning. It does. What is it? It is energy. Define Q. Energy transferred from high temperature to low temperature. This is the definition of Q. The energy that is transferred from high temperature region to low temperature region. This is basically coming from the zeroth law. of thermodynamics, which is A, sorry, um, A is in equilibrium with B, B is in equilibrium with C, oh wait, A is equilibrium with C, B is with equilibrium with C. Then A is in equilibrium with B. This is the zeroth law. Here the equilibrium means thermal equilibrium, which means same temperature. So, of course, when it's same temperature, there is not going to be any heat exchange, right? There is no energy going from A to B. But if A has higher T than B, then the heat will flow from here. That's very simple. That's the zeroth law. That's what it's talking about. And this is the basic law that we use to make a thermometer, right? That's how simple it is. And we bring this concept here. So when you think about Q, there is this kind of physical meaning, but you still can't manipulate it because it's a path function. So we need to think about another way to express heat in a state function way for mathematical convenience. Okay? And back to first law. U equals, delta U equals Q plus W. And if you convert it, it's going to be like this. Q equals delta U minus W, which is going to be delta U minus P, plus P delta V, right? This is Q. And so people are very smart. They just made up this new concept. H equals U plus PV. That's how people just randomly made it up. They just did it like this because they think it is convenience. Why? I'll show you. See, when we make a derivative of dH, then it is going to equal to du plus pdv plus vdp, right? And back to here, del q is going to equal to du plus pdv, right? Here how we got this is we just changed. So this is already a delta term here, right? We changed this to infinitesimal change, that is delta q. Here also we change it to du, here change it to pdv, right? I can't stress enough that this means a path function. Anyway, so when you think about this two relationship, it is going to be same when it's constant pressure, right? Because dp is going to be 0. So dH equals du plus pdv, which is del q, right? So at constant pressure, infinitesimal change of enthalpy is going to be equal to del q at constant pressure. So people are very smart because when we do a material science, normally pressure doesn't really change. Pressure stays constant for most general cases. So dH equals to del Q for general cases. And as I told you briefly in last lecture, H is a state function. So we successfully converted a path function into a state function here, like this. So now we can use the concept of enthalpy as state function kind of expression of heat. The important thing to remember here is that Q has physical meaning. It is the energy that is being transferred from high energy region to low energy region, but H does not have any physical meaning. Well, it does in the later lecture, but here you can kind of understand it like that, okay? So I'm not gonna write it. So H is primarily made up concept. It's a made up concept in order to express heat in a state function kind of way. Now you can see that when a material has H equals to 50 joule, now you add something to it, it became H becomes to 100 joule, then you can say that enthalpy change, the heat state function way of heat, like delta H is 50 joule. You can easily calculate this. You couldn't do that with Q. You cannot say that because Q1 is something, right? You can't, because Q is a process term. It's not a state function. There is no Q1 or Q2. There is H1 or H2 because we made it up. It's just that simple. Okay? So that is enthalpy. Now we are going to finalize the okay, before we finalize, I'll show you another example. So here is an open system. It's an open system. When a material can come in and come out. Okay? Oh wait. In, out. Then how do you write first law? It's going to be like this. U equals. So what is the internal energy change brought from this material coming in? We call that flow work. So when a material comes in, it is going to give its internal energy to the system, which is this much. Remember this? We just talked about it. It's specific internal energy, right? And other than this, it is also going to give mechanical work to the system, right? Because the material itself has its volume. And it is going to do some work to the system. Like this. P. So, to write the total form, it's going to be like this. So, when a particle comes in, this Mi is coming in, then it's gonna give two energy to the system. First is internal energy, second is flow work. So what is that? Now internal energy, this is simple, right? Because of course if this particle comes in, the internal energy of this particle is going to merge into the system. So change from this internal energy change is I times ui equals u. Remember this, specific internal energy of I coming in particle, right? And we can express it like this, because this ui equals ui divided by m. Now flow work is mechanical work done by the particle to the system, which should be uh, expressed like this: P delta Vi. Vi is the change of volume because of this particle. Why there is no minus here? It is because when in terms of this Mi, the work of this Mi is like we talked about, minus P delta Vi. Delta V minus P delta Vi. But it is in terms of this particle. It is going to do this amount of work to the system. The system is going to receive this amount of work. So when we look at the system, it is going to gain this much, the opposite amount of work, right? So we can express the energy transferred by this particle to the system as this ui plus flow work, right? Flow work equals this plus P delta V I, which can be changed into Mi plus P Vi delta M. Here we can, like this, right? Delta Mi is the amount of particle that coming in. Now this is just coming from this, right? Delta Vi equals Vi delta M, right? Because this equals to Vi equals to V divided by M. All right. So for infinitesimal amount of particle coming in, it should be like this: ui dmi plus p vi dmi, and we get the dmi out, which is this. Looks familiar, right? We just derived enthalpy as u plus pv. So the energy caused by this particle coming in should be like this, right? And of course, some particles are going to leave the system, so that is HODMO. Should be minus term, because material is leaving. It's going to take away the internal energy, right? So we can rewrite the first law. So the bone structure doesn't really change. Should be del Q plus del W equals du. Let me write it like this. But here we're gonna have to add the material coming in and out part. So it modified to this way. HI dmi plus minus out H out dm out plus del Q plus del W equals du. The energy is conserved again. Of course, energy is conserved all the time. That is the first law. Modified. This is the general case, general equation of first law for open system, right? If it's closed system, dmi equals to dmo equals to 0. Okay? Now we're going to talk about we're going to talk about CP and CV. What are these? These are capacity, heat capacity, right? In very thorough term, you should call this specific heat capacity. We'll derive this, okay? So heat capacity definition is this. So mc dt equals to q. This is the del q. Okay, so the amount of heat needed to increase the temperature of a system or material, let's say material, of the amount. So definition is amount of heat needed to increase the temperature of a material by per 1 degree or 1 Kelvin per unit mass. So let me rewrite. Sorry, I wrote it kind of confusing way. So definition is amount of energy needed to increase the temperature of a material by 1 Kelvin. Okay? In unit mass. So when you take this, then CV equals to del Q over M dt, which is d del Q dt, right? Let's take the first law, then du equals to del Q plus del W, right? And when we assume it's steady state and no work is done, then du, no. So when we assume no work is done, so this is at constant okay, at constant volume. All right, let's bring this. So there's this system. We're gonna give him heat, and the temperature is going to increase, obviously. But we do this as we maintain the volume of this system. So constant volume, which is isovolumic process. Then of course del W is 0, because remember, like that kind of diagram, and here work is 0, right? Because volume change, there's no volume change. So del W is 0. So du equals to del Q, right? And by definition, C becomes like this, equals du dt. We call this CV. Okay? CV. So specific heat capacity at constant volume. Right? And for constant pressure, of course, there will be CP, right? And at constant pressure, remember we did this. dH equals del Q. Do you remember? We would derive this in the previous lecture. I hope you remember. Let me go through it again. So H is U plus PV, dH equals du plus pdV plus vdP, del Q equals du minus del W by first law, and del Q equals du minus plus pdV. So at constant pressure, this term is 0, so dH equals to del Q. Anyway, so we plug this into the same formula, then Cp equals dQ over dt. Here, dH dt. Here we mind this 2 under bar. It means specific or molar. Basically, they're the same concept, specific or molar. Okay, so that's why we call this specific heat capacity, which is why you can probably notice that the unit of capacity should be joule per mole K, right? Because this is joule per mole, and this is Kelvin. All right, and something worthy of noticing is we use Cp way more than Cv, because as I told you, as material scientists, we are focused on situation where it is constant pressure. We do our experiments with constant pressure, and the volume of the material will change. So we don't necessarily use CV, right? It's obvious. Anyway, now we have the concept of, let me summarize it for you. Summary. First, we talked about, what was it? Specific property, right? Specific, which is basically just, remember this, intrinsic. We want to know the actual intrinsic property of this material. We don't want to know, so let's say, let me use an example. So, China is the one of the richest country in the world, right? Based on the total GDP. But if you average it, it is not the richest. So you can't say China is the richest country in the world. Or some kind of there is this kind of material. So you want to normalize this. You want to know what is the average value. You want to know how much money does each one of them have. You don't want to know the total. Total doesn't really show the intrinsic property of this system. You want to know each and every one, what kind of property they have, right? So this is the key point, intrinsic. Okay, so, and second part was about, what was it? Here, yeah. And then we talked about steady state. or equilibrium, which is a system doesn't change with time. With time. Okay? And third, we talked about enthalpy, which is very, very important concept. Remember, I told you this, of course, it has a physical meaning, but not as obvious as heat. Heat actually has a real physical meaning. It is just simply heat transferred from high temperature region to low temperature region. In the meanwhile, enthalpy is just a concept that we created. Human created this just to make the math more simple and convenient, so they can know like which way to integrate or which way to do the math, because in for heat there is no way to express this in mathematical function. For enthalpy there is a way, right? And fourth, we talked about the heat capacity. Now we are going to solve a problem, okay? To review what we learned. So, there's this furnace, and there is this aluminium bulk. You make this into a thin foil by raising temperature. It used to be 300 Kelvin. Now you're gonna raise it to 800 Kelvin. So you roll it so thin foil. We're gonna ignore this work done here with the rolling. We're just gonna think about how much heat needed to increase this aluminium bulk from 300 Kelvin to 800 Kelvin, and I'm gonna ask you how much heat we need in order to increase aluminium from 300 Kelvin to 800 Kelvin. That is the question. And I'll give you Cp equals to 20.67 plus 238 times 10 to minus 3 T. This is Cp of aluminium. And solve, and wait, and this bulk is 1,000 kilogram. Okay? And this question, you need some kind of assumption in order to solve this question. So first method of solving this question is you take the furnace as the system and furnace as system. Now material coming in and material leaving. This is furnace. And you're going to assume steady state, which means, I told you, du equals to 0. Okay? Now du equals to del Q plus del W. Now del Q equals to du. Why? Why? We are looking at this furnace as taking this furnace as the system. Is there volume change? No, right? The furnace, the system, there is no volume change. So that's why PdV is 0 minus PdV, so del W is 0. Del Q equals to du. Alright? And, wait, I made a mistake, sorry. There's no need for this. right? Um, Sorry, my bad. Just the point is here. The system del W equals to 0, so del Q is equal to du. And this system, the heat required to, in order to, melt this aluminum into thin foil, right? So, del Q, what did we talk about? C d CV dt, right? Wait a minute. Wait, no. Wait. Oh, right. Sorry. I'm totally confusing you guys. All right. Sorry. We assume it's steady state. So the du doesn't change for this. Du, oh, equals to 0. Okay. Then remember first law, right? We derived first law for open system, which is H in Mi minus HOMO plus del Q plus del W du, right? And this is 0, I just told you. And this is 0 because it's steady state. So what is the heat change then? Is MO minus HIMI, right? Then we can just simply divide both sides by same, because MO and MI equals to 1000 kilogram, right? So you divide, then it's like this, right? Okay. And do you remember that I told you this is state function? And what is state function again? We don't need this, right? Because it's not like there are many different stuff coming out or coming in. It's just one, so we can change it like this, right? And I told you that characteristics of state function is dh equals h2 minus h1. Do you remember this? I told you path function, this is not equal, but for state function, it is equal. So we can use this, right? So del Q equals to HO minus HI. Of course, this is final state, initial state, and this is final initial. We just plug this H2, H1, DH, and we derived already that this is CP. You recall that, right? We just derived it. So it will be like this. T1, T2. Now it's easy, right? You just integrate it. Should be very easy. 3730 joule per mole. Okay, wow, that was hard. Sorry for confusing you guys, but I hope you watch it over and over again and solve it yourself. Try solving it yourself, okay? And case 2. No, method 2. We are going to look at this guy as our system, not the furnace. Now it's not a open system anymore. It is a closed system. But this closed system is going to enter this furnace and come out as another thin foil, right? Nothing comes in or out because this is a closed system. Again, it is steady state. du equals to 0, okay? Now, what we're gonna do is, again, first law, delta U equals W plus Q. So Q equals to U2 minus U1 minus W, right? Now, this W is going to be U2 minus U1 minus P, or plus P, right? Because W equals to minus P V2 minus V1. Because this is V2, this is V1. It's gonna be pressed in constant pressure inside this furnace, right? So it should be like this, V2 minus V1. Looks familiar, right? You can rearrange this into this, H1. So again, it is Q equals to H2 as H1. Then it should be the same value as we derived, which is 13730 joule per mole. Notice here is per mole, per mole, per mole. Specific properties. Properties, right? Remember this. Okay, so much for first law and some detailed examples. Thank you for listening. I hope you guys enjoyed the lecture. Thank you.